So here's something you've seen before. Our definition of velocity, uh, subscript here just means that it's actually an average velocity because it deals with what's happening over a whole time interval. The displacement divided by the amount of time it took to make that displacement, and then I just rewrite it a little bit. Displacement is average velocity times the size of the time interval, and the size of the time interval is just the difference between the final time and the initial time. So think about a simple velocity graph now. Constant velocity for a while. Constant velocity from some initial time to some final time. And notice that the length here on the horizontal axis is just that, and this height here on the vertical axis is just average velocity, the value of that constant velocity. So that is the same as the height. That is the same as the width of this rectangle. So this is just the same as height times width of the rectangle here inside the velocity graph, or area inside the velocity graph. And what was this in the beginning? It was displacement. And that's an example of a general rule that relates areas on a velocity graph to displacement. Right? Area is, just by definition of area, a positive number, and that would make this positive. You get positive displacements only if there is a positive velocity, which is what we have in this case. So what we really need to say is that this statement here is true if the velocity is positive. If the velocity is negative, it's almost the same. Let's think about that. So again, a velocity versus time graph, and now we'll say that there's a constant velocity between some initial and some final time. And the value of that constant velocity, now negative, is minus VA. And so we have a constant velocity for that much time. And it's still the case that displacement, this is still true, because this just came from this, which came from the definition of average acceleration. So it's still the case that displacement is that, average velocity times the length of time spent moving. And this number here is still the width of a rectangular area. This number here is negative, which we can just write it as -1 times this height. Right? This height, this distance on the graph, is just the absolute value of the negative velocity. So -1 times that height just gives us our negative average velocity times the width. And so now we see that in the case where there is negative velocity, there's negative displacement because the length of a time interval is always positive, and now this is a negative number. So what we have is displacement equals this, which is just minus 1 times height times width, which is area. And that's true for negative velocities. If we have negative velocities, there's negative displacements. But anyway, this is the important idea is this. It's a relationship between areas on a velocity graph and displacement. The area between the velocity line and the time axis, and between some starting and final times, is either, that area is either equal to the displacement or minus 1 times that area is equal to the displacement, depending on whether the velocity is positive or negative. And the nice thing about this rule is that it applies all the time, not just to simple areas like these rectangles. It applies to absolutely any area. So for example, graph of velocity versus time. Let's say the velocity graph is weird like that. It is still the case that that area between the velocity line and the time axis is the displacement. And even if velocities are negative, even if the velocity line has a funny shape, it is still the case that for negative velocities, displacement equals the minus 1 times the area between the velocity line and the time axis. We'll see other situations like this as the semester goes on. Some kind of area in a graph corresponds to some important quantity. Let's look at an example of this. Let's say start out with some positive and increasing velocity, and then positive but decreasing velocity, and then negative velocity getting stronger, and then negative velocity getting weaker. And let's say, just to keep things simple here, it's all very symmetric. And this is 1, 2, 3, 4 seconds, and this speed here we'll say is 2 meters per second, and then this velocity here is minus 2 meters per second. So displacement is area. The total displacement here between 0 and 4 seconds is just the displacement that we get that corresponds to this area, and then add the displacement that corresponds to this area. So total displacement is just the displacement that happens from 0 to 2 seconds plus the displacement that happens from 2 to 4 seconds. Okay. Positive velocity, so this displacement is just this area, and it's a triangular area. So the area of that triangle is this displacement. And then here's negative velocity. So -1 times this triangular area is this displacement. And this area is what? Well, the area of a triangle is 1/2 base times height. 1/2 base times height. So total displacement is first the displacement we get from calculating this area, 1/2 and a base of 2 seconds times a height of 2 meters per second. And then we add the displacement that we get from this. And this displacement is negative because the velocity is negative. This displacement is equal to -1 times this area. So -1 times that triangular area is 1/2 base height again, 1/2. And the base is again 2 seconds. And the height is again 2 meters per second. When we say that this displacement here, this negative displacement, is -1 times area, we've taken care of the minus sign just by thinking that. We don't need to worry any longer about the fact that this is a negative 2 meters per second. -1 times area just means -1 times an area of 1/2 times this base length times this height length. Length is a positive number. But anyway, look at these. They're equal to each other. So they're both 1 meter. Or this is 1 meter, this is -1 meter, so they cancel each other out. The net displacement over those whole 4 seconds is 0. And then one other example. Let's say simpler velocities this time. Just from 0 to 2 seconds. Let's say we have a constant velocity of 2 meters per second again, and then suddenly turn around, switch to negative velocity, but the same magnitude, same absolute value, same speed. Now -2 meters per second. And let's say maintain that same negative velocity until 6 seconds. So again, the grand total displacement between 0 and 6 seconds is just the displacement over the first 2 seconds, from 0 to 2 seconds, and the displacement from 2 to 6 seconds. Positive velocity, so a positive displacement. This displacement is just this area, and this area is 2 meters per second times 2 seconds. 2 times 2 gives us 4 meters. And then this displacement is negative because it's a negative velocity. It's negative. This is -1 times this area. There's the -1, and the area is 2 meters per second times 4 seconds. 2 meters per second times 4 seconds. And 2 times 4 is 8. A displacement of -8 meters. So in other words, You go forward 4 meters and then backwards 8 meters. So the net displacement, 4 minus 8, is just minus 4 meters. Your final location is 4 meters farther in the negative direction than where you started. All right, now, one other thing that we need to think about, acceleration. Haven't thought about that yet. We've got velocity, which tells us the rate at which location changes, but velocity itself changes also. So we need another number to tell us the rate at which velocity changes. And our definition for an average acceleration looks almost exactly like our definition for an average velocity. Right, the average acceleration is just change in the thing whose change we are measuring, velocity. Change in velocity divided by the length of time it took to make that change. And because it's a rate of change just like velocity is, it's many of the properties of acceleration will be very similar to the properties of velocity. Many of the things we say about velocity we'll be able to say also about acceleration. For example, take a graph of velocity versus time, say like that. That line has a slope, and you know how to calculate the slope. Say you pick 2 points on the line at some initial and some final time, and at some initial time, that was the velocity, and at the final time, that's the velocity that you read off the graph. Slope is just change in velocity divided by, change in the vertical variable divided by change in the horizontal variable. Slope is just change in the vertical variable. Change in anything is final minus initial value divided by change in the horizontal variable, final minus initial time. But of course, that's just another way of writing delta V. And that's just another way of writing delta T. And that, of course, is our definition of acceleration. So almost exactly like we said about velocity. In a position graph, slope is velocity. Here, in a velocity graph, slope is acceleration. Remember, a graph of anything versus time, slope is the rate of change. So in a graph of velocity versus time, slope is the rate at which velocity is changing, and rate of change of velocity is just another name for acceleration. When we're talking about velocity, the direction of velocity is easy to interpret. It's just the direction of motion. When we're thinking about acceleration, which is also a vector, the direction of acceleration is a little bit trickier, but very, very important to understand. Well, let's think about it this way. So let's start with this. Change in velocity. Is, of course, final value minus initial value. Rewrite that a little bit by adding V initial to both sides of the equation. Then we have V initial plus delta V equals V final. So in other words, change in velocity can be thought of, really should be thought of. Change in velocity should be thought of as the velocity that you add to whatever velocity you started with in order to get a different velocity at some later point in time. The extra velocity added on. Now go up here. This is a vector. The only thing a vector can be equal to is another vector. And for two vectors to be equal, they have to have the same size and they have to have the same direction. So the direction of the acceleration vector is the same as the direction of this vector. And of course, the piece here on the right-hand side that has direction is change in velocity. So there it is. Direction of acceleration is the direction of delta v. Easy to say, but it takes a little while to really understand what that means. The direction of acceleration tells you the direction of the extra velocity that is being added on to make the velocity change. Let's take one simple example. Let's say a moving object is speeding up, and of course the velocity means the velocity vector is changing, and like any vector, we can represent any vector with arrows. The arrow represents the direction of the arrow, obviously represents the direction of the vector, and the relative lengths of the arrows represent the relative sizes, the relative magnitudes of the vectors. Right? A velocity arrow twice as long as another one means the longer arrow represents a twice as much velocity as the shorter arrow. So when something is speeding up, the arrow that represents the initial velocity is shorter, and the arrow that represents the final velocity has to be longer. What we're doing is really something like this. Now, when we have this picture that compares the initial smaller velocity to the final bigger velocity, we ask ourselves, what extra velocity do we have to add to the initial velocity in order to change the initial velocity from this to this final velocity? And pictorially, it's easy to see. You have to add that much velocity, and that being the velocity added on. That's delta v, the velocity added on. And so if delta v points this way, acceleration points that way. Acceleration tells you the direction of the velocity that is being added on. That's enough for now. That it takes a while to get used to, so don't want to overload the brain too quickly here. But it's an important idea to ponder, keep thinking about. I'll keep hammering away at it in class and reminding you. Direction of acceleration is the direction of the extra velocity added on in order to make velocity change.